Well, howdy, students. This is going to be 14.3, and this is going to finish out notes for this unit. And in this video, we're going to talk about the strengths of acids and bases, and with that, the theory of acids and bases. There's actually several different definitions. And then we're going to look at equilibrium, capital K, problems on how to write expressions for weak acids and weak bases. So there are several different theories and definitions of acids and bases. The first one we're going to look at is called the Arrhenius definition for acids and bases. So when an Arrhenius acid ionizes, this is when we get a hydrogen ion. So an Arrhenius acid is considered a compound that contains hydrogen that ionizes to yield an H plus in solution. Now, an Arrhenius base is a compound that ionizes to yield hydroxide. So this is kind of our initial definition, but Arrhenius acid is going to give off an H plus. Arrhenius base is going to give off OH minus. So this is probably our easiest definition, and it's just because we're looking for two specific things, H plus and OH minus. Now, our second definition is known as the Bronsted-Lowry definition for acids and bases. Now, Bronsted-Lowry definition for an acid is when there's a hydrogen ion being donated, which we also call the proton donor, somewhere else. A base is what we call a hydrogen ion acceptor. So this is where the definition gets a little bit different from Arrhenius. So if we're looking at this example with ammonia and water, we're going to produce NH4 plus and OH minus. And what we want to know is what happened to the hydrogens. So if I look at NH3, there are 3 hydrogens, and NH3 turned into NH4. And you'll notice that water went from H2O, and now it has 1 less. So what happened was water donated an H plus to ammonia. And by definition, if we donate a hydrogen, water would be the acid in this case, and because the base is accepting of a hydrogen, ammonia, NH3, is the base. So with Bronsted-Lowry acids and bases, we have what we call conjugate acids and conjugate bases. So a conjugate acid is a particle formed when a base gains a hydrogen ion. Now, a conjugate base is a particle formed when an acid loses a hydrogen ion. So if we look at the picture, for NH3, the base was the one that accepted, and the acid was the one that donated. So on the other side of the equation, we had ammonium NH4 plus and hydroxide OH minus. So we can actually label these as a conjugate acid and a conjugate base. So ammonium NH4 plus is the conjugate acid because it was the one that gained the H plus. And the conjugate base, hydroxide, is the one that got rid of or donated the H plus, if we were going backwards. Okay, so I think we're going to label here which one is the conjugate acid and which one is the conjugate base. So HCl becomes Cl. So the HCl lost a hydrogen. So on the left side, we call it the acid, which makes chlorine the conjugate base. So we call these conjugate pairs because they're always connected and they're generally opposite. So if one's an acid, the other's the conjugate base. If one's the base, the other's the conjugate acid. H2O gained a hydrogen, which makes it a base, which makes hydronium the conjugate acid. Next one, H2O, and we're mixing it with acetate ion. Well, the H2O lost a hydrogen, which makes it an acid, which makes the hydroxide a conjugate base. And then, of course, acetate, because it's gaining the hydrogen from left to right, it's the base. Acetic acid would be the conjugate acid. What about the ion product constant for water? We have H2O plus H2O yields hydronium and hydroxide. Doesn't matter which water you pick because they're both the same. So choose one and label it. In this case, this water that we chose is the base because it's gaining a hydrogen, and hydronium is the conjugate acid. H2O to hydroxide, it is losing one, which makes it an acid. The hydroxide would be the conjugate base. We have a term for a substance that can actually be an acid or a base, and that is called amphoteric. Amphoteric is a substance that can be both acid and base by Bronsted-Lowry definition. So water can be an acid, meaning it can lose H plus to become OH, but it can also gain and become H3O plus. So we have two examples there. You'll see that water loses a hydrogen here to HCO3, which is hydrogen carbonate, and it becomes OH. And then here, we're going to take and strip that hydrogen away from acetic acid to form hydronium. So this is an amphoteric substance. And our final definition for acids and bases would be Lewis acids and bases. A Lewis acid and base, specifically a Lewis acid, is an electron pair acceptor. So if we are accepting electrons, which we're kind of changing here because the last one was the hydrogen, which is a proton. So now we're looking at the actual electrons. If we accept a pair of electrons, we have a Lewis acid. If we donate a pair of electrons, we have a Lewis base. So here's an example. H plus plus H2O yields H3O plus. So how do we know what happened here? The hydrogen went to the H3O plus. Well, the H plus is the the acid, because it is going to accept a pair of electrons from water. H2O would be the base because it's going to donate a pair of electrons. AlCl3 plus Cl minus. AlCl3 is going to be the acid because it is going to accept an electron pair, and Cl minus is going to be the base because it is going to donate electrons. Here are a list of common acids and common bases. Towards the end of this video, we're going to talk about the strength of acids and bases, and we want you to know which ones are strong and which ones are weak. So we'll come back to this list at some point and label which ones are strong and which ones are weak. You'll notice the hydrogens on the lefts of all the acids, and then you'll notice the hydroxides on these compounds. Now, we do have some compounds that don't have to have hydroxide. They may be classified as a base based on Bronsted-Lowry or Lewis. Strengths of acid and bases. Concentrated and dilute are different from strong and weak. So you can have a strong acid and a strong base, and they can both be concentrated or dilute. Strong acids are completely ionizable in aqueous solution. So here are our strong acids: HCl, HNO3, and H2SO4. So real quick, let's go back, and I actually want you to label those. So strong, strong, and strong. And there are others, but these are the three that we want you to know. Weak acids only slightly ionize in aqueous solution. And so here are the weak acids: H3PO4, which is phosphoric acid, H2CO3, carbonic, and HC2H3O2, which is acetic acid. These actually ionize only slightly. And because of that, we actually form an equilibrium reaction. And we can write out an equilibrium expression based on this equation. So we have this equilibrium constant value, 1.8 times 10 to the negative fifth, which is specific for this reaction. Strong bases dissociate completely into metal ions and hydroxide ions in aqueous solution. Here are our strong bases: NaOH, KOH, and calcium hydroxide. So I'm going to go back and label those real quick. So these three were considered strong. Weak bases do not dissociate completely. So NH3, CH3, NH2 are examples. Again, we get an equilibrium expression here, and that particular equation has a equilibrium constant value of 1.8 times 10 to the negative fifth. And you'll notice that this is Kb, and the B stands for base. So what's the difference between strong acids and bases and weak acids and bases? Well, it has everything to do with how they dissociate. Strong acids dissociate 100% into ions, and weak acids and bases dissociate only a small amount of time. So when we have weak acids, we can actually write equilibrium expressions. For acids, we call them Ka values. For a generic weak acid, we have H, and the A is some sort of formula. Breaks apart into an H plus and the rest of the formula. So this is how we would write our expression, products on top over reactants. We learned this in the last unit. The larger the Ka, the stronger the acid. We don't have Ka values for strong acids because we use up all of the reactants. That's why there's no expression. In each H, a diprotic and triprotic acid has actually a separate Ka value. So if we have more than one hydrogen that can be dissociated, we'll actually have 3 different equilibrium expressions that we can write. So for this one, here's our equation. Products over reactants is our equilibrium expression. And we're going to throw brackets around these guys for concentration. For weak bases, we're going to do the same exact thing. But remember that pure liquids don't get included, neither do pure solids. So you'll notice that H2O does not show up in this equilibrium expression. The larger the Kb value, the stronger the base. So what do Ka and Kb values tell you? Well, they tell you the relative strength of the weak acids that we encounter.